Today, we're exploring an engineering assessment of a unique pipeline scenario, one that's been out of service for some time and is now set for reactivation. However, this isn't your typical steel pipeline. Instead, we're dealing with fiberglass spoolable line pipe, commonly referred to as FSLP, specifically designed for oil emulsion service. An important factor to consider is that this pipeline operates at elevated temperatures around 45 degrees Celsius. Elevated temperatures are critical because they significantly increase risks for fiberglass spoolable line pipe. Compared to fiber wound spoolable composites, FSLP inherently possesses lower resilience and is more prone to degradation, even when operated within the manufacturer's recommended parameters. Thus, rigorous integrity assessments and detailed evaluations are essential. Fortunately, there have been no known failures to date. However, the absence of historical failures does not equate to an absence of risk, particularly with composite materials like FSLP. Considering the pipeline's extended operating history, there's a high probability that some damage has occurred, making it particularly vulnerable upon reactivation. To evaluate this thoroughly, we deployed advanced TRIAGE risk assessment tools from AbaData, enabling a deeper analysis beyond basic inspections. You can imagine this as giving the pipeline a thorough health checkup, one that can uncover hidden damages, potentially leading to future issues. Our findings highlighted several key risks: thermal cycling and expansion. Elevated temperatures can cause axial movements and potential buckling, especially at mechanical joints and at termination riser and right-of-way connections. Material vulnerability. Fiberglass composites are susceptible to microcracks and even delamination due to repeated temperature fluctuations and operational stresses. Operational stress. Pressure surges and severe slug loading, common in oil emulsion pipelines, can exacerbate existing vulnerabilities. These dynamic conditions trigger cyclic impact loads and applied stresses capable of causing fatigue-related failures, particularly in compromised pipeline sections. To proactively mitigate these risks, we recommend the following actions. Robust hydrostatic testing. Perform hydrostatic pressure testing at twice the pipeline's normal operating pressure to identify any hidden defects or compromised integrity. Targeted direct inspections. Use hydrovac equipment to expose and visually inspect critical pipeline segments, particularly at origin points and termination riser connections, to assess structural conditions thoroughly. Enhanced operational monitoring. Implement continuous and diligent monitoring protocols from the outset, including daily inspections of above-ground risers. Vigilant oversight during initial operations is critical for detecting subtle movements or bending conditions indicative of developing structural concerns. These proactive steps surpass mere regulatory compliance. They reflect a commitment to ensuring safety, reliability, and operational excellence. Remember, this engineering assessment isn't just a regulatory formality, it's a strategic roadmap for informed and proactive decision-making. That's our session for today. If you're part of a team planning pipeline reactivation, take this as your cue to dig deeper. Ask questions, challenge assumptions, and remember, small insights today can prevent big problems tomorrow. Stay curious, stay safe, and I'll catch you in the next episode.